And yeah, to do a reduction, okay, a full addition of H2, are there other options?
The H2
The rainy, actually I don't know how to pronounce it. As soon as you said that, I'm like, I would call it rainy, but I honestly don't know. Do you know that it's Ronnie? No, okay, I was just curious. Okay. The H2, and I'm going to have to fall back to how I pronounce it, but it could easily be rainy nickel. For this particular reaction, it needs to be preferenced.
But does that do, I thought that reduced alkenes, or that wrong?
It can reduce alkenes.
Oh, okay, gotcha.
It does a lot of different reductions. But if you throw in the dithiol beforehand, what the rainy nickel will go through and do is do your reduction the way you want to. Okay. So that one also does this. Okay. Is that it? No.
B also does the full reduction.
B also does the full reduction, and I believe, though I'm not positive on it, that that's known as the Clemmensen reduction. Okay, and that's the zinc mercury amalgam in the presence of HCl. Okay. So this should be problematic. This should harken back to a different reaction that we've yelled about a whole bunch, and by we I mean me, of course. Okay. What other reaction did I yell about that had 3 possible reagents to use?
The addition of OH and H.
Yeah, the addition of H and OH, and that's incredibly, that screams multiple choice. Okay? Because depending on the outcome of that reaction, you would choose different reagents. Okay? We've got the exact same system here. We've got 3 different reagent systems that do the exact same thing, but they do it slightly differently. Okay? So because of that, we need to understand what is special about each of those reagents and what could potentially cause problems throughout the course of the reaction. Okay? So if we did this, erase the bromine, doesn't matter, all 3 work just fine. Okay? But if we bring that back, now we've got a dilemma. Why do we now have a dilemma? What is that bromine doing?
It has the ability to leave.
It has the ability to leave, which means this carbon is very electrophilic. So if I want to run this reduction, I want to run it in such a way that I don't react with that electrophilic carbon. Because if it does, I could get side reactions that I don't want. I just want the carbonyl being reduced away.
So something that targets ketones?
It's not a ketone right now, it's an aldehyde.
Oh,
Okay, and we could say targets carbonyls. All 3 of those reagents target carbonyls.
first?
Not necessarily, and so therein lies the next issue. Okay, if we got rid of the bromine, not a problem. The bromine there is now potentially a problem. What is the potential problem that the bromine brings in?
It's another positive that any negative hydrogens could react with.
It's another positive. It's another electrophilic site, which means what do we not want to see in our reagents?
Nucleophiles.
You want to find a reagent that doesn't have a nucleophile, because if it has a nucleophile, what is it likely to do? It's going to react with the bromine, and that then becomes a problem. Okay? So we could go through and look at each of these reagents and say, well, do I see a nucleophile? Okay, so the Wolff-Kitchener, do I see a nucleophile?
I'd say so.
Okay, where do you see the nucleophile?
Well, there's the OH, and there's the nitrogens will have lone pairs.
So the Wolff-Kitchener is extra problematic, because you have the oxygen, which can act as a base or a nucleophile, and the nitrogen. Both of those would be phenomenal nucleophiles, which would screw up the whole reaction. Which suggests
That's not a good answer.
that's not a good answer. What happens in the next one? This one becomes harder because it's not using elements we're typically used to seeing. Where did you look? Yeah.
Up there.
Why'd you look at the periodic table? Up there. Jiminy Christmas. Todd, or can you help me?
To look at sulfur.
Yeah, elaborate.
See its electronegativity. See how much its valence electrons. I don't fucking.
Okay, so that's fine. So you're looking for your. So it is kind of like God periodic table tell me something. Okay. Do we see anything that could potentially be pulled from the periodic table with respect to the sulfur that might help us out?
Strength in an amplifier.
Sort of.
It's
Where is sulfur on the periodic table?
third row.
True. Third row. What was that?
It's right below oxygen.
And what's special about it being right below oxygen?
They're gonna have similar qualities.
They're going to have similar qualities. Those are families. This goes all the way back to either 130 or 151. They have the same bonding patterns, which means if I'm looking at sulfur underneath oxygen, oxygen, I know when it forms bonds, has 2 lone pairs, which means what's the sulfur got? 2 lone pairs. And if it has lone pairs, I can then ask the question if it's a nucleophile.
Doesn't have to be strong.
Okay? And it doesn't have to be strong, right, for this particular scenario, but it is a nucleophile. What did I not want?
Nucleophile.
Which would suggest
Bad.
that's a bad idea. Which then means
They really got one left.
it's got to be the Clemenson. Okay, we could do process of elimination on a test. I'm okay with that. Okay, but we're not on the test right now. Why does the Clemenson work?
No nucleophile.
Okay, we've effectively lost the nucleophile. Really all we have is the acid is H+. We got a little bit of problem with the chloride. Okay, and you're looking at now kind of competing bromide versus chloride, nucleophilicity within that potential system. Okay, but that's relatively minimal in comparison to everything else. The zinc and the mercury are what's coordinating the oxygen, what's facilitating the acid reactions that gets the hydrogens onto our structure that runs the whole reaction across the board, which ultimately means the Clemenson does not introduce the issue of a nucleophile. And since it does not produce that issue of a nucleophile, there's our reagent. Okay? So how could the question get rewritten?
Which one's the worst?
Okay, we could do which one's the worst. That gets real problematic. Because both A, B, and G, I just started saying letters. A, C, and D are all bad answers. Deciding which one's the worst becomes a really weird kind of question at that point. Okay? So how else could we modify it?
You could maybe add another living group to the substrate.
But another leaving group is still going to produce that same nucleophile issue.
You could change which one's the best.
What if I made it a carboxylic acid?
Oh, okay.
What are acids going to do? React with bases. So do we have any reagents that act as bases? Well, damn, the Wolff-Kitchener acts as a base. Okay? So what we're trying to do is effectively look at the secondary reactivity of each of those reagents and say that when I choose them as a reagent, it shouldn't have something else that it would react with. Kind of make sense?
Does the rainy nickel one, does that act as a base?
There's one paper.
It does have the lone pair, so it has the potential to act as a base. It's a fairly equilibrium-based reaction, so it's not going to be a huge factor in that
Well, then
case.
which one would win out? The Clemenson? Because, a strong acid isn't going to be a strong base, so.
So strong acid could work. We could probably also get away with the rainy nickel process.
Okay.
Okay. We do have some potential things that we'd have to worry about. The sulfur is what's attacking the carbonyl. Do I have another carbonyl? Yeah. Well, the Clemenson is also going to have that issue. So what's the reactivity of the carboxylic acid versus the aldehyde?
It's greater.
The acid is more reactive? And an unintentionally ambiguous question. Right? What we're referencing is the carbonyl reactivity. Which carbonyl is more electrophilic, the aldehyde or the carboxylic acid?
Oh, the carboxylic acid.
Why?
Because it's connected to more electronegative elements.
Connected to more electronegative elements, and therefore that is a larger positive, right? Yeah? What's on the oxygen? What can those lone pair electrons do? Which does what to the positive charge?
Fuck you. There's no other response.
Sometimes I wonder if like the audience voices get recorded. Usually they don't, but you're close enough and your volume is loud enough, it might actually get recorded. And I watched YouTube's gonna like cancel me. You have too much cursing in your videos. I was like, dude, I've done it like twice. It's the audience that doesn't like me.
Twice? That's an understatement of the year.
In a lecture. Okay. So what you should go back and do is look at those reagents, and the textbook does a good job of saying the Wolff-Kitchener has this secondary effect. Okay. The Rainey-Nickel has this secondary effect. The Clemenson has this secondary effect. So they actually organize those really, really, really nicely, I believe, in the textbook to say, watch out for those secondary chemistries. Okay? Because what you're starting to move into is synthesis. Not just how do I get this reaction to work, but which reagent is best at getting that reaction to work. Okay? Which is another higher order level of thought, but that's why you're in second semester. You have the ability to now be thinking at a higher order. Make sense? What do we say the answer was? Okay, just checking. Next question.
32.
This is another one where I started to get carried away, and I think there might be a typo within the question, so we've got to look at it a little bit more carefully.
It does say typo not solid written.
What?
It does say that typo not solvable as written. It's not the case.
Oh, okay. Oh, for the
For 32.
the not share, the not open edit document, because this is the open edit document, and I don't see that. So I think I acknowledged that and put that in there. So why is it not solvable as written? What changed? What happened in this reaction?
You got another. You oxidized.
Broke a pipe on
Oxidized.
it, gained
Hey, it didn't break a pipe on it, just oxidized.
Oxidize means you increase the bonds to oxygen. If I look at the reactant side, I have 1, 2, 3 bonds to oxygen. If I look at the product side,
I was looking at 33, dude. I'm going to be honest, that's my bad. Yo, that's on me.
did you ask for 33 or 32?
You asked for 32.
Okay,
Yeah,
just
no, I
checking.
was just reading that like it was 32.
Okay. I was like, what are you talking about? Like, didn't we cover this?
No, that's my bad.
Okay. So cool. Not oxidation. What changed?
Reduction.
You gain a methyl on the left, and then you lose a methyl on the right.
Oh yeah, I did use methyl.
And then it's just, it could be flipped.
There it
It's
is.
split. Is it?
If we take this structure and flip it,
It's split. So the oxygen that lost the pi bond and it gained a hydrogen.
Damn, fuck that.
1, 2, 3, 4,
Sucks.
5, 6. 1, 2, 3, 4, 5, 6.
So it just flipped and yeah, that's literally all that happened. Oh my god. This is terrible.
Nasty. Good job.
Thank you.
Right? Which then means what happened? What changed?
You just reduced that oxygen over there. That's it.
Right.
I mean that carbon.
We've added a hydrogen and a hydrogen, added H2 while adding or removing an oxygen bond. Yes, is a reduction. So we could think about all of our reduction reagents. So if we think through our chemical reactions, what chemical reactions do we have access to?
There's substitution,
Substitution, elimination,
addition,
addition, acid base. You said that.
radical.
Radical. Did I say reduction?
What would you say reduction?
That's a good point. Why would I say reduction? Okay. Knowing that it is a reduction reaction is okay. Don't get me wrong. Okay. But that's a different classification, and that can mess with how you go through and approach things. So I just want you to be aware of that shift in language, because we do introduce reduction and oxidation reagents, and they're kind of sort of separate. They're like a subclass of our addition reactions. Okay? So that's all I'm trying to point out. Okay? So we are adding H across the pi bond, or H2 across the pi bond. So what reagent would do this?
PCC? Maybe.
PCC did what? Is oxidation.
Shit, that's
This
opposite.
is yeah, it does the opposite. This is one of the reasons why I don't like trying to memorize my reduction and oxidation reagents, because I think it's very easy to swap them, particularly in the heat of the exam.
You're super right.
And that's a personal issue for me. If you don't have that problem, that's okay. Unfortunately, Anthony, I think you do have that problem, right? And so you should be a little bit more careful behind that. So there's lots of reduction reagents.
I mean, we just went through a couple of rainy nickels.
Cool, we just went through 3 reduction reagents, but all 3 of those reduction reagents did what?
Full reductions.
Full reduction, complete wash of the carbonyl. I'm not losing the oxygen. So Clemenson, Wolff-Kitchener, and the rainy nickel aren't going to be useful.
And then the only other option on there
Is the what?
is the CH3.
So
If we decide to do
Grignard
that,
provides a negative carbon. The negative carbon would come in and react. I don't want a negative carbon to come in and react.
well, that's not the only problem. It would, like,
Okay, and maybe you're saying negative carbon because you're looking at the answer choices, but what did we establish about the answer choices?
they're wrong.
They were wrong, so let's not look at the answer choices. Let's think more broad. What reagents do we have that could potentially complete this? And yes, that is a significantly harder question because you're now not doing process of elimination. You're trying to think back to all those reagents. And if you at any point you're like, dang, I don't remember these reagents and I have to look them up, that is okay. Where's your list of, damn, I don't have this memorized? Write that down. Okay? So that you can review that. Wouldn't any acid react to the oxygen? So ultimately the acid is going to provide H+. So I completely agree. The acid would go through and protonate. I'm not going to draw the whole rest of that structure. The oxygen would be positive. That's an oxygen. Oh, I can fix that. Okay. We could do resonance, but then we have a positive carbon. What would I need to put in there?
Negative.
A negative hydrogen to replace that. But what is the negative hydrogen most likely to do?
Act as a nucleophile.
Act as a base and remove that hydrogen, that positive hydrogen you just put on there. Okay? So you've got the right flow behind this. If we're thinking about the reactivity, we need a negative hydrogen to chill in there, and I need a positive hydrogen to go to the other spot. Unfortunately, the flow that you picked was backwards. So fix it.
Would it be like BH3 and
Okay? BH3 and THF. What is BH3 and THF? How does it react? How does it react? And that becomes the harder question.
Well, no, sure. Produces a negative hydrogen. That's how it reacts.
Okay? So one of the things that we might memorize is that produces a negative hydrogen. Okay? So you've now just provided an awesome multiple choice answer for me to go through and put on the exam. Because that's not how it reacts. Yes, it eventually produces negative hydrogen, but first, how does it react?
It has to react with positive.
The boron acts as an electrophile. A nonpolar pi bond dumps electrons into the boron, which forces the hydrogen out to react. Okay? BH3 and THF with the carbonyl as a reagent actually does not work particularly well. Okay? It is something that sometimes gets tried, but it's not great. Okay? That was actually one that I think in a short answer somebody provided years ago, and I was like, wrong, maybe. And I went and had to look it up, and I was like, the yield on it is crap.
But it does do the reaction, just not very well.
Yeah, so I think what I ended up giving them was half credit, and it was like, you just BS'd your way to a half a point. Good luck. That's better than 0, but that's a half a point for that particular scenario. How can I guarantee I have an H minus?
Is it NABH form?
How about we make that BH4? As soon as I make it BH4, that boron can't act as an electrophile anymore, and what's happening is it's trying to offload the electrons tied to a hydrogen. Right? So sodium borohydride could work well to offload that hydride to our carbonyl. Okay? Typically, when you run sodium borohydride, you run it in a protic solvent like methanol. Why do we run it in a protic solvent like methanol? Where do you get the H plus? You pick it up from the solvent. Okay. Sodium borohydride is a neat reagent because typically when we think about H minus, we would think about it acting as a base. And if it's acting as a base, what must not be present?
An acid.
Acidic hydrogens. So that would be really, really problematic. Except the reaction, the boron stabilizes the hydrogen enough that we don't get much of that acid-base reaction, and instead it reacts with the carbonyl for the vast majority of scenarios. Are there other reagents that would have done this same thing?
Probably.
Cool. Since Anthony said probably, you all have to come up with another answer. Say it again.
The lithium aluminum hydride.
Lithium aluminum hydride. Effectively the same thing as sodium borohydride. Where is lithium on the periodic table?
On the left.
Above sodium. They have the same chemistry. The hydride is hydride, like there's nothing going to change there. Where's aluminum? Right with the boron. All of the chemistry is identical. Right? So it's also going to supply H minus. There's a slight issue with the lithium aluminum hydride, though.
Less stable.
It's much less stable. Why? That could be a good short answer question. So what's the difference between sodium borohydride and lithium aluminum hydride?
The amount of valence electrons.
The amount of valence electrons are spot on identical. They're all in the exact same families.
Give me shots.
Lithium and aluminum, all really not electronegative.
Minor effect. Why would I care about the lithium? Is the lithium what's changing the chemistry of the hydrogen? No. Okay. So again, we're asking for what's the difference between these two reagents. What is the difference between sodium bor versus lithium alu?
The lithium and aluminum. Oh, there are two metals versus not two metals? Is boron a metal?
Metalloid. And technically it's not a metal, actually. I don't think it even falls in the metalloid category.
Aluminum is under it, so it's going to have different.
Okay, so when we make the comparison between the reagents, we want to compare the similar things. Aluminum and boron are related to each other within the family. So what's the difference between boron and aluminum? Yes, we could go to electronegativity, but where should we go first?
The orbitals that they have access to?
Size, which is an effect of orbitals. Right? So if aluminum, well, what's that difference in size? Sorry.
Significant.
Aluminum's bigger than.
Aluminum is bigger. If it's bigger, how well can it hold on to that hydrogen? That bond just got longer. That's harder to hold on to that hydrogen. Which means when I look at borohydride versus aluminum hydride, the aluminum hydride is more active as a negative due to the size differential between our boron and our aluminum. Well, what's the difference between the sodium and the lithium? This one becomes much harder to deal with.
The sodium is bigger than the lithium.
Right, so there's again a size difference. How is that size difference affecting the hydride?
It doesn't.
Oh, and that's nasty. It doesn't. But it does change the overall chemistry of the reagent. how could that sodium and lithium affect the overall chemistry of the reagent if they aren't connected to the hydrogen? What charge are lithium and sodium?
Positive.
Positive. Where might those positives interact?
Negatives?
What negatives?
The oxygen.
The oxygen of our carbonyl. Okay. Lithium being smaller creates a shorter bond to the oxygen. Yes, it's an ionic bond, but it is a shorter bond. Because it's shorter, that means the bond is
Stronger.
stronger. Does oxygen want to be positive?
No.
What does it do to the pi bond?
Breaks it.
It starts to weaken it. So if I throw lithium in here, that weakens the pi bond more than sodium. So lithium aluminum hydride, the lithium messes with the pi bond, makes it faster to react. The aluminum makes the hydride faster to react. Lithium aluminum hydride is a much more active reagent because you're changing the atomic characteristics of those reagents. You're going in and looking at those size effects and how those size effects affect the overall reaction. That's pretty gnarly. Okay. How much is it? Significant. You cannot run the reaction lithium aluminum hydride in the presence of methanol because that hydride is now so uber reactive. What's it going to act as? A base, and it will immediately deprotonate the methanol. And if it deprotonates, do we have the hydride to attack our carbonyl? No. Right? So let's just get rid of the methanol.
Well, then we don't have the hydrogen to put on the oxygen.
Okay? So we've got a couple things come up. You say, well, where do I get the positive hydrogen? Where do I get the positive hydrogen? Is I run a second step where I add the positive hydrogen. You're like, that's a cop-out. That's not a cop-out. That's a fair response acknowledging the chemistry behind that. So I can follow it up with an acid. I still have an issue with the solvent. So what solvent do I want?
Aprotic.
I want a solvent that is aprotic. Okay? And I probably still want it to be polar because
So it'll dissolve.
so it'll dissolve all of these very polar things. So I'm probably looking at an aprotic polar solvent. Okay? So could I have sodium borohydride and methanol, lithium aluminum hydride, let's pick diethyl ether. Okay? Now we have two answer choices for this overall reaction. Here's answer choice A, here's answer choice B. Answer choice C is both, or bath, depending on how you want to pronounce the A. What's your answer?
I feel like this is a trick, but
I feel like this is a trick. What did you suggest? C, because what do the reagents do? They both supply H minus, they both supply H plus. Shouldn't C work where both those, why are you saying no? You already felt like there was a trick, but you're saying no.
There's acidic hydrogens on our substrate.
wah, wah.
Look back to the substrate. The substrate had another functional group on it. That other functional group was an acidic hydrogen. I don't have to worry about the acidic hydrogen coming from the solvent. It's coming from my reagent. And since it's coming from my reagent, I cannot use lithium aluminum hydride because the lithium aluminum hydride is going to target that instead of my carbon.
Damn.
Which means the answer is
Hey,
A.
that was a whole lot more thinking than I wanted to do.
You're welcome.
You know, when you're saying one fucking word, it sounds so wrong.
Does anything I say sound right?
Yeah, that's like a
Yeah,
fucking
thank you.
Did say E would react with
The lithium aluminum hydride would react with the alcohol in our starting material, not with the carbonyl. Okay. I will sort of add a caveat to that. Sometimes you'll see systems where they will still choose to use lithium aluminum hydride to run this reduction, and it works. But then why are we saying it's a bad idea? How did they make it work?
They probably changed the reactant? Or do you mean this exact
This exact thing. They could still make lithium aluminum hydride do this reaction.
Oh, maybe they added something to lower the charge on the hydride.
Nope.
No? Okay.
Exact same reagent, all the setup. How could we get this reaction to actually work using lithium aluminum hydride? a little bit outside the box. Right? And I don't think I've ever seen the ACS do this, but I have seen it in literature where someone does a synthesis, and probably what happened is they didn't have the other reagents, so they just said, F it, we're going to fix it by doing this.
You protect the alcohol somehow.
Don't even have to protect it.
Make the hydride bigger.
When we run a chemical reaction, we tend to assume 1-to-1 ratio. If I add in a ton of the lithium aluminum hydride, what's going to happen? It's going to immediately remove the hydrogen off my alcohol. Yeah.
But then the rest of it
The rest of it can then go react with the carbonyl. How do I get my hydrogen back? Well, step 2. Add H+, and now you're all fine. Right. So I would like to call that a cop-out, but I think that's actually a pretty smart approach to trying to adjust and be like, well, dang, we didn't have the reagents, let's just work with what we've got and force that to happen. There's a couple scenarios like that where you overwhelm the balance of the reagents intentionally because you know the reagent's going to do something you didn't want it to do. Right? Solvent choice, though, we're still stuck. You can't overwhelm the solvent. You can't use a protic solvent here and then add a ton of lithium aluminum hydride because the solvent's there in a huge excess to begin with.
So you're
Right.
using so
So,
much.
yeah, the only way this works is when the problem that you've got is on your starting material, not in your solvent. So you have to use a polar aprotic solvent. Kind of makes sense? Actually, I think I saw that on someone's test. I was like, that's really rude. I get it, they're right, but it's still really rude. Okay. If we go through and look at the rest of the reagents, what did A do? What would A do to the reaction?
It would act as a base nucleophile, something like that. I can't remember.
It would act as a base, nucleophile, or an acid, maybe an electrophile. Yep. Completely agree. That's fair game. They would probably do one of those things.
All of them would fully reduce the ketone.
Okay? So way to just end run the whole slow question process. A, C, and D are all full removal of the ketone. They take it all the way down to the alkane. Okay? Yes, we might have a problem with that alcohol, potentially messing with the chemistry, okay, as secondary things, but at this point, I don't want to elaborate on thinking through all of that. Just want to recognize what's happening to the carbonyl. What would B have done?
Would have added on carbons.
It would have added on a carbon. So our final product, come on, would have been this.
Yeah, but it also would have deprotonated.
Oh, this is the other case where I've seen the excess. It would deprotonate that alcohol. If we did a 2x excess, it would deprotonate, then it would do the attack, then we'd add the acid. But you're right, that acidic hydrogen there, classically, if we see that acidic hydrogen, we would call that a no reaction. Kind of make sense? You happy?
Yeah, I just have one question. So, like, you said all 3 are just the ketones, so the alkanes. So,
ACD, yes.
so if the alcohol group wasn't there and it was just the ketone group, then would it just be like 3 methyls to do the alkane? Or if it reacted with any?
So if we, because I didn't want to go through that part of it again, so we're going to erase that part. Okay. If we ran ACD, what would happen? Let's see, 1, 2, 3, 4. 1, 2, 3, 4. We're good. What's that? You get the full reduction. Okay. With the alcohol there, that adds some functionality that we would have to be careful with. For instance, in a particular scenario with the Clemenson reagent, because the Clemenson reagent adds a strong acid. What is the strong acid likely to do? React react with the alcohol to make water a great leaving group so it can leave, and then chloride's a decent nucleophile could come in and react. And so you could end up getting a substitution as well as doing the Clemens reagent. Okay. So adding that alcohol on there is pushing you to say, okay, do I need to worry about that or not? Do I have to worry about those secondary reagent conditions? That's one of those things that I'm telling you that you need to look up and make sure you're aware of the kind of secondary issues that could pop up with the Rainy nickel, the Clemenson, or the Wolf condition. Right? And we've already addressed some of them.
So C wouldn't do a substitution. So have the CL.
C, if we ran C, it would go through and do the full reduction, so we'd lose that oxygen, and more than likely, that would turn into a chloride. Okay. If I didn't want that to happen, I shouldn't do that. Okay. Theoretically, that's kind of a bad synthesis, because when we think through our synthesis reactions, typically what we're trying to do is one thing at a time. Okay. If it so happens that we can cram like 6 things in at once, cool. That usually means we get to attach our name to it. So maybe we should try that. Somebody should draw this little structure and be like, ta-da! This is now the Anthony reaction, because it did a reduction and a substitution. What? Yeah. Next.
Is what I put for 33 right? Because you said just reread my answer, and I think it was because I used the words ketone and then aldehyde instead of just saying aldehyde. I changed it back to just be aldehyde.
So wait, you changed the question? You changed your response?
Yeah, because I originally said the alcohol wants to become a ketone, so I changed it to aldehyde because it's an aldehyde. I thought that's what you meant when you said reread my answer. Like, is what I put correct? Or?
What you have right now is fine.
Okay.
Yes.
And then, I guess 28 then?
Where's my cursor? Was that a sigh?
Yeah. Looked at it once and like, I don't know, as soon as I saw you see it, it's just.
Okay, so named reaction, you're likely to see it specified as an aldol. Okay, so you could leverage that and say, okay, I need to memorize the output of an aldol reaction. Okay, because very often we're concerned about what the final product is. Less so, we tend to see questions on mechanisms. Okay, I do ask them, but you're probably more likely to see what's the reactant, what's the product, what are the reagents kind of questions. So if you spend some time to say, aldol means this, you now have an answer. Now it's just a question of finding it. Right? Within this, I do want to be a little bit careful. These are R groups, so those could really be anything out there. So for this particular question, we'd have to be a little bit more specific behind it. Okay, so we went through and set this up. Aldol, here's our second carbonyl underneath. 1, 2, 3, 4. 1, 2, 3, 4. Erase that out. Complete the double bond. Now it's just a question of changing the alignment of this structure to match the answer choices provided.
Isn't aldol supposed to have an aldehyde and
Aldol does do that. The aldol very commonly is followed by what? A condensation. And what does the condensation do? Loss of the alcohol, loss of a hydrogen, gain of a pi bond. So if we actually color-coded this a little bit, the aldol is the formation of the sigma bond between those two structures. The condensation is the formation of that pi bond. That pi bond is going to be the loss of our alpha hydrogen off of our starting carbonyl, and the loss of the OH, our alcohol, that was from our attacked carbonyl compound. With it drawn out that way, hopefully that helps you see that the answer is should have been a little faster than that. I have an aldehyde here, right? There's the carbonyl. Is that an aldehyde? Is that an aldehyde? Does this have an aldehyde? Is that an aldehyde?
Oh, would you look at that? That's exactly what I was thinking in my head the answer would be.
Right. So pattern recognition becomes very, very powerful. Look for those kind of pieces to evaluate that. Okay. It does require a back and forth. Okay. That back and forth is kind of dickishly as that was presented.
3 times.
Oh, God damn it.
4.
Right. What I went through and did was looked at this structure and then tried to evaluate all of those answer choices as quickly as possible, thinking about what functional groups am I going to see. I want to see a carbonyl with a pi bond. Okay. That would get rid of this one and this one. That leaves me with C and D. The difference between C and D is where the carbonyl is located, internal versus external. I can look here and say that's external. There it is. So you're trying to swiftly align to those pieces. Okay? Would you like me to show you how I typically see students go through and answer this question? Sure, cool. Why not? I think it has a carbonyl and an alcohol in it.
No?
That's what I see on the exam. Just the answer is A. Why is the answer A? And for those people being like, you just said the answer wasn't A. I know, that's the problem. Okay. When you draw out the product, you have a way to answer the question. If you do not draw it, you cannot see it. It's amazing. Okay? Just because your work is not graded does not mean you should not show work. You should write something down allowing you to process through. Because if you don't write something down, what you're now doing is spending all of your time looking at wrong answers. Like, well, it's not all of my time. 3/4 of your time spent on the exam is looking at wrong answers. And if that's where you're spending your time, guess what you're going to do? Pick the wrong answer. Okay? If you don't know, that's a whole nother ballgame. Now, theoretically, you should have moved on and eventually come back and been like, well, shit, I don't know what to put. Now you can try and do whatever testing strategy games you want to try and play with this to try and figure out what it is. It says aldol, I think there's a carbonyl and an alcohol, I'm going to pick that. Okay, that's fine. That's wrong, but you've acknowledged that you don't know anything about it. If you know something, write it down. Okay? Spend the time to write it down. I don't have enough time. You do have enough time for that. What you don't have enough time for is sitting there thinking, I think I can do this in my head. You can't. I'm sorry.
Feel called out.
You should be called out. Okay? You can't do that. What you have to accept is that you need to write it down. You don't have the practice to be able to manipulate these structures in your head that fast. So don't. Stop it. Write it down. I've said it before, and I'll continue to say it probably for the rest of my existence as a teacher of this class. The highest scores have writing for everything.
I don't know how they write that fast and to be legible.
That, unfortunately, I would have to kick back to your lower classes, like your high school and your elementary classes, that didn't force you to write. You don't have the practice. That's what it comes down to. You need more practice in writing. That's how it becomes legible. And if you get it, that's fine. But yeah, I would bet, based off of how long it's taken me to force you to write anything down for this anyway, you don't like writing. Okay? Why you don't like writing is, I don't want to go there. Okay? But you don't like writing, and so you're avoiding that process. That's hurting your grade. Okay? Does that matter to you? I don't know. That's on you. You get to decide. Because I'm not sharing what your grade is. You could have an amazing grade in the class and everybody be jealous of you. That's fine. You would have a higher grade if you wrote it down. That's all I'm saying. If you're like, but if I have an A, what's higher? Shut up. Not the point. Make sense? Okay. What next?
27.
The rest of y'all just that confident in this?
I mean,
Usually ask questions that I also have, so it works out.
Okay, so you just decide to let him do all the work for you?
Pretty much.
I
Thank you.
think it's more of a work smarter, not harder type of situation.
I'm gonna take your guys' solvents.
Oh my goodness.
Fair enough.
You can do the work for me.
Because you know there's a fun little workaround, right?
What's that?
So there's our overall mechanism-ish. What reagent do we need?
Base.
Yep.
We need a base, right? Right there. Or all of these bases,
Yeah.
which means
Any that won't work thus far.
all of them work. What happens in step 2?
It reacts with itself.
It reacts with itself. To react with itself, what must be present?
This excess of the starting material?
Excess of the starting material. Does that set off any alarm bells?
That we don't
Would
see
hydride
excess.
be a bad one because it'll just keep reacting with the starting material?
Hydride is such a strong base that what is it going to do?
Constantly deprotonate.
It's going
all
to
of the
deprotonate
acidic
all
hydrogens.
of our acidic hydrogens. Okay, and for the record, that doesn't mean pull more hydrogens off of already negatively charged structure, but what it's going to do is pull hydrogens off of the undeprotonated structures. Which means,
It'll
do I have this red structure if I use sodium hydride? No. All I have is the negatively charged structure. Would I expect that negatively charged structure to react with a negatively charged structure? No, which means can the second step happen?
No.
No. Ooh. So the selection of base is very important to the overall reaction. So sodium hydride does not work, which is now going to set up another dilemma. Because if sodium hydride doesn't work, what else is then wrong?
D.
D.
So now between A or C, it's the better base.
so then
Is it the better base? Is that? And what do you mean by better? Like stronger base or the one that allows the reaction to work?
I guess you'd want the weaker base then, huh?
Why do you want the weaker base?
Because you don't want it to depronate everything. You want it to just depronate that one thing.
You only want a small amount of deprotonation. You actually want this acid-base reaction to be
Reversible.
reversible. Sodium hydride was a bad choice because
It's not reversible.
it's irreversible. Do you know about the reversibility with the NH2 and the OET?
Oxygen is reversible.
Why is the oxygen reversible? How would we decide whether a reaction was reversible or not? What do we have to compare?
Stability of the product versus stability of the reactant.
Cool. Which reactant are we looking at?
I guess oxygen.
Elaborate a little bit more.
A.
Good enough. We're looking at the negative oxygen. So on the reactant side, that negative oxygen is the most charged, is the most reactive. That's our primary focus. When we look at the product, what are we looking at? The charged carbon. Well, which one's more stable, oxygen or carbon?
Oxygen.
Oxygen, which would say
That it's reversible.
no, it's a little worse than reversible. We got a head shake no. What are you head shaking no at?
Oh, that's not gonna happen. Oh shit.
The reaction just straight up doesn't happen. Okay? Except
Except it does. Is that what he's about to say? Oh.
the resonance stabilization suggests that we also have this structure floating around within solution. And if we look at that structure, these two resonance contributors, which one should we be looking at to compare stability?
The most stable one.
The best one.
The best one, which we would say would be
Green.
the green one, because we have the negative charge on oxygen versus the negative charge on carbon. So when we compare, we're comparing a negative oxygen to a negative oxygen. Is there a difference in energy? No, which means that reaction is
Reversible.
reversible. In an equilibrium, we get some of both. Okay? So cool, with the negative oxygen, fair game, that can go both ways. What happens if we switch that up and drop in the NH2? The NH2.
It's a negative nitrogen versus negative oxygen.
Which one's more stable?
The negative oxygen.
Negative oxygen, which means
That
That would
It's
be
not
more
reversible.
towards the product.
this is more towards the product. We don't get any of that starting material still floating around. NH or NaH, sodium hydride, and our sodium amide are both stupid strong bases. That's how they're talked about in the lecture videos. As stupid strong bases, they are irreversible. And if they are irreversible, that means we're going to push all the way across to that deprotonated carbonyl. And if we push all the way across the deprotonated carbonyl, we don't have any of the starting carbonyl compound to continue to react. Right? It is a little bit more nuanced than that because, of course, the speed of the reaction and all that come into play, and we would generate some of our final product here, but our yield's going to be pretty piss poor because it's almost exclusively all going to turn into this structure, which isn't going to do anything useful for us, and it just stalls the reaction until we move into the workup phase where we add the acid to neutralize everything and we go right back to our starting material. Right? So when we run our reactions, we have to be cognizant of the activity of our individual bases and how those things react. This pushes to our kinetic versus our thermodynamic, which was a huge part of this particular unit. The answer here is going to be A, the NaNH2 is not a good choice because it is an irreversible process. Yay! Right? So this is one of those things where we have to think really carefully. Because I will fully admit, when I've seen this question, I've been like, oh, it's all the above, you just need a base. And you go, you know? Yeah, that's going to be irreversible, and then I don't have anything to actually continue to run the reaction. Okay? That continuing to run the reaction is a whole nother beast, because when we look at it, okay, sometimes the very first response is, well, where the hell did I get those carbons? Product has 6 carbons, my starting material only has 3. How does this work? Does it work because you have 2 of your starting material to run the reaction, which is very oftentimes implied in that reaction cycle. Kind of, sort of? I'm going to take that as a yes. Okay? And, according to that clock, I'm done on time. That clock is 3 minutes slow.